welcome back. Thanks for joining again. Yesterday, I started to explain you how we can find recurrences for given sequences of numbers. And we faced the problem that sometimes we have too little data to make a linear system that has more equations than unknowns. And in that case, we get a kernel of dimension greater than 1 that contains infinitely many elements that are rubbish and just a single element that is the recurrence that we are looking for. And the question is, how can we possibly identify this interesting element in this kernel? And I already alluded to lattice reduction algorithms. There are plenty of them. This is an active field of research in computer algebra, but the most classic one, and that will do the job in our case, is the LLL algorithm. So let me quickly give you an idea what this algorithm is doing. So we are talking about an integer lattice that is generated by vectors in z to the m by doing integer linear combinations with coefficients in the integers. So we get a lattice, and the LLL algorithm computes a different basis for the same lattice that involves short vectors. Well, what is short? I mean, typically shorter than these input vectors. It's depending on how you set up, you want to find the basis with the shortest vectors, or you want to find a basis with reasonably short vectors. There are many variations of this. And so how does this look like? Here I draw a picture, and let's take these two vectors. If you look carefully, they are not exactly parallel, and you see it from the definition here. So they generate a lattice. How does this lattice look like? Well, we get all these points. So when we take this arrow, we go to the other direction, we get this point, and by doing the combinations. And obviously, this is not the shortest basis for this lattice, but the basis with the shortest vectors is given by the two blue vectors, W1, W2, and this is exactly what pardon?
You do not assume that V1, VL are near V?
Well, yes, typically we assume this. Yes, otherwise, yeah. Okay, and so we would like to find these blue vectors. And okay, so what we observe is that it has to do with orthogonalization. So we see that the two parallelograms that are spanned by these two bases, they have the same area, but the blue vectors are more orthogonal than the red ones. And this is actually the basic idea of this LLL algorithm. It is a variant of the Gram-Schmidt orthogonalization that is adapted to this integer setting. Okay, so what can we do with LLL? Here is one classic application that is very fundamental and basic: detect integer relations. So if you have given real numbers x1 to xn, and you suspect that there is a nice relation between them, a linear relation with integer coefficients, or let's say rational number coefficients, but you can clear denominator, so let's say with integer coefficients, then this is called an integer relation. And you want to find these coefficients a1 to an. Maybe you have a number that you can compute to a certain accuracy, but you have no idea what it is, but you guess it could be a combination of pi and theta of 3 and whatever constants. Then you can use this to make a guess what is the closed form of your number. So LLL gives you candidates for such integer relations, and it works as follows. You choose an accuracy, so a number of digits that you want to deal with. Let's say m is 10 to the d, and so let's say if some numbers you have given numerically, then you would choose d to be the number of valid digits that you know. Then you take, you build the lattice that is generated by these vectors vi, where each vi has the ith unit vector of length n, and in the last entry you put the scaled value of xi rounded to the next integer, or taking the floor, it doesn't really make a big difference. And then you apply LLL to this set of vectors. So these vectors, they are very long because they have these entries here that are multiplied by this big number m. And if there exists an integer relation, then this corresponds to a combination, to an integer combination of these vectors vi with these numbers ai. And so we expect that these numbers are somehow nice and small. So if there exists an integer relation, this corresponds to a vector that has in the first n entries has these a1 to an, and in the last entry you have somehow the error that you make from the truncation, because here in the last component of these vectors we have these numbers. Yes, and so you apply LLL, you look at the output, and if you find that the first vector is significantly shorter than the others, this is a good indication that you have found something meaningful. And so if you want, you can try this. Here I cooked up an example of a number that is given to 50 digits, and I tell you that this is a linear combination of these constants, and you are asked to find the coefficients. It's a very simple exercise. You just have to do what is written here. Okay. Sure. There's, I mean, yeah, here what I will show you in the exercises, I will use the plain LLL implementation, but of course there are lots of programs for such integer relation finding, and somehow this is the down-to-earth thing what I'm doing, but there's much more fancy implementations like PSLQ and whatever. Yes. Okay, now back to our guessing problem. We want to find a vector with small integer entries in the kernel of our matrix, and we have to be careful. There's a problem because what we did before, when we did the naive guessing, we computed a basis of the kernel as a Q vector space. But now we want to work over the integers. That means we want to work over a Z module, and a basis for that module is not simply obtained by taking a basis of this Q vector space and removing all denominators, which we could do, but we really need a basis for this Z module. But luckily this can be computed, for example using the Hermite normal form. So this works as follows. You take your matrix, this A should be this matrix M. A is M. You attach the unit matrix of the suitable size, then you do the Hermite normal form algorithm, and then you get a matrix that is in echelon form, and you take all the rows which have an appropriate number of zeros. That is, if the matrix A has the dimension m times n, then you want to have n zeros here, so that these rows here have length m. And then all the rows that are denoted by k here, they form a Z module basis of the kernel of M or A. This gives us the following algorithm, and this is joint work with my colleague Manuel Kauers. So we input the first values of a sequence A0 to A sub n, and we choose an order and a degree for a recurrence. and the algorithm either finds such a recurrence that involves short integers or it fails. So first we compute the Z module basis of the kernel. Well, if there is no kernel, then we immediately fail. Then we apply LLL to these basis vectors. We get a new basis, W1 up to WL, and we can return the recurrence corresponding to the shortest vector, W1. Of course, in practice, you may compare how much shorter this vector W1 is compared to the others, and the bigger the gap is, the more confidence you have that what you found is reasonable. And yeah, so there's implementation and different variants. You can tweak the algorithm a bit by choosing different bases in your ansatz for the recurrence, not just the standard monomials, but the binomial basis or something else. We can do homomorphic images in Chinese remaindering to speed up the calculation. And well, in practice, you usually don't know what is the R and the D. You want to try all possible combinations, and then you can set up the implementation in a way that it reuses results from previous computations to make them more efficient. But all this is quite technical, and I don't want to bother you with this. So let's look how this works in practice. So here is an example where we have applied the Hermite algorithm to find a basis of the kernel of M. And here I show only the first two vectors. And so we see here the vector, and the length of the rows here tells the size of the integers. So these are vectors that have small integer entries here and then very big ones here. So this is how it comes out from this basis computation with the Hermite normal form. And actually these are just two, there are more in this example which I computed. They are about 20 or 30 or so. Or I think even 40. Now we apply LLL. And so now I show the result that we get from taking different number of terms from the sequence. So in this particular example, 28 turned out to be the minimum possible number of terms that I need to take in order to find the recurrence. And in that case, I get an output, here many vectors in the LLL basis. And if you look very carefully, you can see that the first one has entries that are a little bit shorter than the others. But it's not really significant. If we give more terms of the sequence, let's say 33 terms, first of all, the kernel has a lower dimension. So if you count it, you will find that now we have, since we increased by 5, we have 5 vectors fewer. And we see that now, since we use more data, the difference in the length of the coefficients is more significant. And the more terms we use, the more striking this difference gets, and the more confidence we have that the recurrence is correct.
So if you use n equals 33 and 34, these two leftmost vectors are identical.
Only the first one is identical, and all the others are probably changed.
And when they are identical, it's not already certificated or something?
No, it's not a certificate. Of course, it could be a coincidence. Also, I agree, it's very unlikely, and we are very convinced that if we find twice the same thing, that it's even more significant. But of course, it's not a mathematical proof.
But
all this is absolutely non-rigorous. I mean, even if you have enough terms for not having to use this method, but do the classical guessing, even then you don't know if the result is correct, right? So there's no certainty here. If you have to do like Polya, first guess, and then you have to think how to prove it.
I don't want to be long, but for me, having twice the first vector with two different values of n is more a strong hint than having a shorter vector, a short gap between the first and second.
Well, yeah. Yeah. I will tell you other checks that we can do to convince ourselves that the result is correct in practice. So here's a particular example, some sequence that we found in the OEIS. And these are the first, I think this is the one that I used for the other pictures. So here we see the first, 30 terms that were used for guessing. And the recurrence that was found by the algorithm is this one. Now, on purpose, I displayed it like this, that you see if you the number of bits to write down these two things, the sequence terms and the recurrence, looks almost the same. And this should, of course, make you suspicious. Can this be? And this recurrence doesn't look particularly nice. So the question is, can we trust this result? And actually, when we entered this recurrence into the OEIS, we got an angry email by Neil Sloan saying, in the text of the paper, you say the coefficients are small, and au contraire, he uses even French. In fact, the amount of data in the generating function is comparable with the data in the original 35-term file for the sequence. So this is what we observed. If you print the recurrence and the data, the number of digits is about the same. When this happens, surely you should be worried. I am very worried, and I think he uses GF for, he means recurrence, needs more justification. In fact, it looks wrong. I use GFun all the time, and when the generating function looks like this, like something you would find in the dumpster behind a restaurant, then I would not even consider it. Okay, so we had to address this, and luckily we were able to convince Neil that our recurrence is most probably correct. First, what you can do, you can use this recurrence and compute more terms of the sequence, right? And if that was a dumpster recurrence, what we would get are rational numbers, right? If you take a random sequence of numbers and a random recurrence, and then you have to divide and you get rational numbers. But no, we get integers, and they fit very nicely into this picture. So this is very convincing. Well, maybe even more convincing, and now this is a matter of taste. What convinces you more? If you factor the coefficients of this recurrence, you see that the polynomial coefficients, they're actually not as ugly as they look when you print them in expanded form, but they are actually very nice, and they have a lot of very small factors that, of course, would not happen if that was just an artifact. Yes, okay, so we could convince him. And so this is now the data that we computed for these balanced matrices. So this is the data for balanced binary matrices of dimension 8. No, I think 6 or 8. 8, I think 8 times 2n. Yes, B4, yes, 8. 8 times 2n matrices. These are the first 110 terms. And if we apply the guessing, we find the recurrence. It has order 9, as you can see here, and polynomial coefficients of degree 36. And, I mean, it's kind of the same picture. Already here, the coefficients are factored. You can guess. And so, what I want to tell you here is how much we can gain. So, if you want to guess such a recurrence with a naive algorithm, you have order plus 1 times degree plus 1 is 370 unknowns in your ansatz. So you need, because you have to build the matrix, you would need 379 terms of the sequence. Using this idea of order degree trading, that you try to guess a recurrence, let's say, of order 12, but degree only 20, that would make your ansatz having fewer unknowns. And if such a recurrence exists, you can find it with fewer terms, and then you can use that to construct this one that you want. So playing with this, we found that you need 266 terms with this classical trick of GCRD guessing. And now with the LLL-based guessing, you can get down to 110 terms. Also, you should consider that when I double the number of terms, let's say from 110 to, okay, this is more than double, it's not that I double the information, but since the numbers get longer, I even multiply the number of information that I insert by 3 or 4, whatever. And so here, if we compare the bit size of the recurrence, and I did only the coefficients of the recurrence, is about 45k, and the numbers that I enter have 70k, so it's not very tight, but it's kind of comparable and gives me an indication that we should not expect to get much better.
But isn't the case that when you have all these small binomial factors, n plus 2, n plus 4, n plus 5, maybe there is a more compact relation for before n divided by some gamma of alpha n plus theta?
Well, yes, this was, when on the previous slide, I said you can choose a different basis. So instead of putting the monomials n square, n cubed into your ansatz, you can use shifted version, for example. And if you do that, I will demonstrate this in the exercises. You can make the coefficients of the recurrence a bit smaller and then, be more successful. Of course, if you detect that your sequence, let's say every sequence member is divisible by the central binomial coefficient or whatever, of course, then you should employ that and simplify your sequence and be more successful in the guessing. Or if you have a guess, like, let's say you expect that the leading coefficient involves the factors 2n plus 3, 2n plus 5, 2n plus 7, of course you can include it in your ansatz. But this is very much ad hoc. It's hard to make this into an algorithm. Okay, again, here's some exercises. Okay, no exercises here. Okay, so then there's some experiments with OEIS sequences. So we applied this algorithm to all 350,000 sequences in the OES. And so this was to get an idea how much gain we can expect in average. So we try to identify examples that we can test on. So we look for sequences that have at least a significant number of terms and which seems to be D-finite, so we can find the recurrence with classical guessing, but that are not too simple and also not too large, because then this algorithm takes too long. And here comes the exercise. So use this LLL approach to guess a recurrence for P3. Oh, something has been messed up. I don't know. I don't know, this conclusion is okay, but the pictures were missing, but I can tell you it's about, in the best cases, we can reduce the number of data to between 30 and 40%. This is what we observed in this example that I showed you. And in many cases, you can get 50%, but then there are also examples where you don't improve anything. Okay, so conclusion for this part is we proposed a method for guessing recurrence equations. I should say this algorithm is applicable to medium-sized examples. If you have a sequence where you know 1,000 terms, you cannot use that, because then the LLL computation will be way too expensive and it will not finish in reasonable time. But let's say you have a sequence for which it takes exponential time to compute the next term, and you have 50 terms, and somehow you would need 100 terms, but this is completely out of reach. Then you're maybe willing to spend an hour on this program to get the recurrence instead of trying to compute more terms. This is what I said, we can reduce to 50% or sometimes even less. Here is the example where we went from 266 to 110. down. And yes, we have found quite a few recurrences for sequences in the OEIS. As we discussed, this is just a guess, absolutely non-rigorous. You have to verify independently if you want to have a theorem. And of course, there is this notorious sequence of 1, 3, 2, 4 avoiding permutations that somehow nobody knows how to compute more terms. And okay, admittedly, also few people believe still that it could satisfy such a recurrence. But yeah, just for fun, we tried, and of course, it was unsuccessful. So no news on AV1324. Good. This was the end of the second part. There's still 2 parts to come. I know, this is not just the end. So we had this game, and for those of you who had the fun to play it, here's the solution. But as I said, it is not really difficult. And I shall come back to these kind of matrices later. So now comes the part 3 about D-finite functions in creative telescoping. As a motivation, I give a random selection of identities that can be proven or dealt with these methods. So we can do binomial sums, multi-sums, prove identities of combinatorial type. You can evaluate integrals that involve special functions, like here the Gegenbauer polynomials or the Bessel function on the right-hand side. You can do identities where you have a mixture between summation and integration, like this orthogonality relation of Hermite polynomials. We can compute diagonals of rational functions or diagonals of any power series. We can do constant term extraction of, again, rational function or of powers of Laurent polynomials. So the last one is not an identity, it's just, well, it's 2 different ways of writing this thing. And, okay. Yes, so this whole theory is based on a seminal paper by Doron Zeilberger that is called the Holonomic Systems Approach to Special Functions Identities from 1990, and this created really a big branch in computer algebra, and a lot of progress has been made since then, and a lot of useful things can be done with this theory. I introduce a few basic notions that maybe you anyway know, so maybe we can go quickly through this. So function f of x is called D-finite, differentiably finite according to Stanley, if it satisfies a non-trivial linear ordinary differential equation with polynomial coefficients. So we have f prime, and the coefficients here are polynomials. So examples, if you have a constant that is D-finite, polynomials are D-finite, the exponential function is D-finite sin x, algebraic functions are D-finite, and many more. Why are we interested in D-finite functions? It's a very important and rich class of functions. Many functions fall into this class. By the way, they are equivalently called holonomic functions, so maybe here and there you see the word holonomic. It's just the same. They satisfy so-called closure properties, as I will show on one of the next slides. And in symbolic computation, they provide a very nice data structure, because the fact that such a differential equation requires to give only finitely many initial conditions to specify the solution uniquely, and also the equation itself is a finite amount of information. This enables you to store these objects in a computer. And all these operations, of course, can be executed algorithmically, so you can implement it and do it without hand calculations. So here is a non-exhaustive list of functions that fall into this class. And if you are familiar with special functions, you recognize many of them: trigonometric functions, hypergeometric functions, orthogonal polynomials, whatever. Finished reading? Okay. Here, about closure properties, if you have two D-finite functions, then also their sum is D-finite. And the proof is simple linear algebra. If you want, I can show you on the next slide. The product is again D-finite. Note that here it's not written the quotient. We can take the integral, the antiderivative is again D-finite. Well, this is easy to prove. You just replace every derivative by the next higher derivative in the differential equation, and then it will be satisfied by the antiderivative. We can take the derivative of the function. It is again D-finite. We can do substitution of an algebraic function into a D-finite function and get a D-finite function back. And if you do this substitution into the identical function, you see that immediately that algebraic functions themselves are also D-finite. I don't know, shall I go through the proof? It's a simple linear algebra argument. So you have f and g. You want to define h that as the sum of f plus g. You want to show that this is D-finite. So in particular, you have to identify the coefficients of some differential equation that this h satisfies of some order that is called d and is not known yet. And so if you insert the definition of h into this equation, you get this. And then you use the fact that both f and g satisfy differential equations of certain orders. So you can rewrite this d's derivative of f into a linear combination of f, f prime, and so on up to the order d1 minus 1. And the same for g. And then you collect terms. You get something in fi, I from 1 to d1 minus 1, the same for the g. And this is supposed to be 0. And this is if and only if these coefficients here all vanish. And since they depend on the unknowns that we want to find, you can just solve for this. And if you choose the d, the order of the differential equation for h appropriately, you get a linear system that has more unknowns than equations, and you will find something. Yes?
What's the meaning of the square?
Oh, the square stands for some expression that is too ugly to be printed here. Yes. Yeah, thanks. Good remark. Okay, so in this case, you find that you have to take the new order is just the sum of the two orders. Okay, so to wake you up, let's make a little quiz. Here I print a few expressions, and I ask you to decide which of them are D-finite. So I give you a few seconds to think about it.
You have f in the long list.
I have?
As a function in the long list of special parts.
Ah, yeah. Yes, you remember. Erf was there. Yes? So then you think the first. Who thinks this is D-finite? Raise your hand. Yes, this is the majority. Majority always wins. So we declare this to be D-finite. But it's easy to see, as you say, we know that Erf is a D-finite function. I told you that exp is a D-finite function. What we do is we substitute a rational function. This is just a special instance of an algebraic function. And we multiply, and we have learned that closure properties is multiplication. So everything is fine. What about the second? Who thinks this is D-finite?
There is a problem with the inversion.
Right. So I just, don't look at me when I raise my hand. I just motivate you to make your decision. Doesn't mean that I vote for a D-finite. Right, this is not D-finite because the inverse of the hyperbolic cosine is not D-finite. Next one. So who thinks this is D-finite? It gets more difficult. Now there's more undecided people. So, of course, I'm very mean. I constructed in a way that you get trapped. So you think, we just learned that division is not allowed, and here the exponential is in the denominator. But of course, I constructed this on purpose. In this case, because the exponential satisfies a first-order differential equation, and for such expressions that are called hyperexponential, we can invert. So this one is D-finite. And the logarithm, there's no problem with the logarithm. So this is D-finite. So what about the next one? Arctangent of exponential. Who thinks this is D-finite?
Exponential is not algebraic.
It's not algebraic, you're right. And this is not D-finite for this very reason. And last thing, exponential of arctangent. Is this D-finite? Who thinks this is D-finite? Very few. You think there's a pattern? You're absolutely right. This is the proof. Yeah, but this was the meanest, because of course arctangent is not algebraic. But what makes it D-finite is again has to do with the fact that the exponential satisfies a first order equation, and the fact that the derivative of the arctangent is a rational function. So if you differentiate this expression, you get exponential of arctangent times a rational function. And of course, you can find a relation between this one and the original function. Very tricky. So you see, it's not so trivial. Here's an exercise. If you want, you can, for those that have a green check mark, you can try to derive this differential equation that these expressions have to satisfy. Okay, so for computer algebra, it is more convenient instead of equations to deal with operators. So let me quickly recall this notation. So I use dx to denote the differentiation operator with respect to x. So dx applied to f is f prime, and dx squared applied to f is f double prime, and so on. And then I use this notation k of x dx to denote the polynomial ring in this symbol dx with coefficients in the rational functions of x, and k is whatever field we need, q or c. Okay, and I use the angle brackets because this is a non-commutative ring, as you see from the Leibniz rule. So if you have the product dx times x and you want to switch the order, you have to add 1. According to x times f in parentheses prime is x times f prime plus f, Leibniz rule. Or more generally, you can write it like this. If you have a whatever rational function r and you want to commute it with d, then you get the r prime here. And so as an example, here's the differential equation for Legendre polynomials, second order differential equation. If you write it as an operator, it looks like this. Okay. So some closure properties are nicely stated in terms of operators, and also the definition of D-finiteness. So we can say a function f of x is D-finite if and only if there exists an element in this polynomial ring, in this operator algebra, that is not 0 and that kills the f. This is equivalent to saying that f satisfies such a linear differential equation. And now about the closure properties. Let's assume we have L1 that annihilates f and L2 that annihilates g. Then what can we say about the integral of f? Well, this is what I told you before, that we replace every derivative by its next higher. This corresponds to taking the product of this operator L1 times dx from the right. So if you apply this operator to the integral, the dx and the integral, they will kill each other, and you are left with L1 applied to f. If you want to compute the operator that annihilates the sum, f plus g, it's the least common left multiple of the two operators for f and g. And actually, this capital L not only annihilates f plus g, but actually any linear combination with arbitrary constants. And this can be easily seen, because if L is the least common multiple of these two, that means you have an M1 that you multiply from the left to L1, and an M2 that you multiply from the left to the L2, such that these two are the same. And well, and then it's obvious that this L has to kill both f and g, and therefore also any of their linear combination.
May I make one question? Do these left common left multiplier exist in which
Well, here in this kind of Ore algebras, we will later see also shift, and so it's guaranteed that they exist in general Ore algebras.
Difficult algebra, it's not clear.
Yeah, no, it's not clear, and it may be difficult, but here it's easy to compute. We can transform inhomogeneous equations. So we have a differential equation where the right-hand side is not 0, but something else that is also D-finite. We can transform this into a usual D-finite representation by finding an annihilating operator for this right-hand side h, call it m, and then the product m times L kills the f and the h, and so then this gives a homogeneous differential equation. And what we needed for the guessing that I didn't explain in detail, the order degree trading, the underlying principle is this one. So if we find two operators, L1 and L2, that both annihilate the same function, then we can compute their GCD, more precisely their greatest common right divisor, and this also annihilates f. So this is the principle of this guessing, where I find a higher order recurrence, and hopefully more than one, and then I take the GCRD of these two recurrences, and then with a very high probability I get the lowest order, or at least a lower order recurrence for the sequence. Okay, this about D-finite functions. Now, the very same comes for p-recursive sequences, so now we can go really quickly. So a sequence A of n is called p-recursive if it satisfies a non-trivial linear ordinary recurrence equation with polynomial coefficients. Here it is, an plus 1, an plus r, and the coefficients are polynomials. Examples: the constant sequence, polynomial sequences, the Fibonacci numbers, the factorial, the binomial coefficients, harmonic numbers, and many, many more. And the features are, of course, that this is an important and very rich class of sequences, and we also call it p-finite or d-finite or holonomic or many other names. It's closed under many operations. These are called closure properties. It's a very good data structure in symbolic computation because it allows us to specify the sequence using only finitely many initial values, and also the recurrence involves only a finite number of bits, so it's very easy to store in a computer, and everything can be executed algorithmically. Next slide. Again, you see a lot of examples of sequences that are p-recursive, and there's a lot of intersection with the previous list because some functions in this list are both d-finite in some parameter and p-recursive in another parameter, like here Legendre polynomials. They depend on a discrete parameter n, and it's p-recursive with respect to this n, and it has another argument x, and they are d-finite with respect to x. And we see many combinatorial numbers, Motzkin, Lucas, whatever. Okay. Closure properties: if an and bn are two p-recursive sequences, then also their sum is p-recursive, and the proof is the same as for d-finite sequence functions. The product is p-recursive. And now, not the integral, but the indefinite sum, so the antidifference is p-recursive. So any sequence Sn that satisfies the difference Sn plus 1 minus Sn is an, so this is the discrete analog of the antiderivative, and it works by the same trick. And instead of algebraic substitutions, we can do integer linear substitution of the index. And p-recursiveness is preserved. And again, we do a quiz. Here I wrote a few sequences, and I ask you to make up your mind which of them are p-recursive. So, first sequence, the square of the Fibonacci numbers. Who thinks this is p-recursive? Everybody, yes, you're right. Who thinks that the Fibonacci numbers at index n square are p-recursive? Nobody, you are absolutely right. Who thinks that the gamma function evaluated at n over 2 is p-recursive? Half. Yes, half are right and half are wrong. It's p-recursive, and the recurrence has to jump in steps of 2. And the sequence of prime numbers, who thinks this is p-recursive? Of course, nobody. Everybody knows that the sequence of prime numbers is not p-recursive. It's too ugly, it doesn't satisfy any nice recursive relation. Okay, exercise. For those that are p-recursive, derive the linear recurrence that they satisfy. Not difficult. And again, we use operators to denote these recurrences, and it's the very same. So Sn is the shift in n that transforms an into an plus 1, and Sn squared makes n plus 2. And we denote the ring of all operators with coefficients in the rational functions by kn Sn, and again, it's non-commutative. In this case, the commutation relation looks like this. So if you have Sn times n, and you want to bring the Sn to the other side, you have to do here n plus 1. And this holds for any rational function r of n. You replace n plus 1 if you jump to the other side of the Sn. So we can look at the 3-term recurrence of the Legendre polynomials. We have Pn minus 1, Pn minus 2. First we have to shift the whole recurrence by 2 so that we don't have negative shifts, and then you get this operator that represents this recurrence equation. Everybody happy? Good. Oh, yeah, of course, then now comes this slide. So we can say an is p-recursive if and only if there exists an operator L in this algebra, so that L of an equals 0. And if we have two sequences that are annihilated by L1 and L2, then L1 times multiplied Sn minus 1 from the right annihilates the indefinite sum, the antidifference. The LCLM annihilates the sum of the two sequences. And again, any linear combination, and the proof is the same as before. If you have an inhomogeneous recurrence with right-hand side a p-recursive sequence h of n, then also the sequence is p-recursive by the same trick. You find the annihilator of the right-hand side, you multiply it to the operator of the recurrence, you get a longer recurrence for the sequence that gives the homogeneous equation. And if you have two operators that annihilate the same sequence, their GCRD in that algebra gives another recurrence operator that annihilates the sequence. Of course, there is a close connection between these two concepts. So a sequence is p-recursive if and only if its generating function is D-finite. This is a very well-known fact, and I am sure you all know how to prove it, so I will not prove it. Let me quickly mention that also the Q case falls into this general framework. So in the Q case, that means we consider Q difference equations that are equations that involve this shift that you either write with a variable x that is mapped to Q times x for some symbol Q that you introduce, or you write it in the form Q to the n and then is mapped to Q to the n plus 1. Sometimes people write it in terms of Q differential equations, so where this Q differential is defined by this quotient, and you see it's basically the same as here, this shift. So examples, there's a generalization of the Pochhammer symbol, the Q Pochhammer symbol, the Q binomial coefficient that we have already seen yesterday. And there are Q versions of the trigonometric functions and of many special functions like Q Bessel functions, Q Legendre polynomials, Q Gegenbauer polynomials, and so on. Yeah, this was just to mention this. I will not use this so much in the following. And to come to the end of this introduction, let me say that this works in the multivariate setting also. So far we have talked about the univariate setting. So in the continuous case, you can think of functions that depend on several continuous variables, and then you, instead of a single ordinary differential equation, you look at a system of partial differential equations, and this must have certain properties to be maximally overdetermined to call the function D-finite. I will make this more precise on the next slide. in a discrete case, instead of a one-dimensional sequence, we have a multi-dimensional sequence A sub n1 to nr. And again, there is a certain condition that it must satisfy multivariate linear recurrences that are sufficient to make this D-finite. In the Q case, we have multivariate expressions for Q equations. And then you can mix everything together. So you can look at functions that involve a certain number of discrete parameters, n1 to nr, and another set of variables that are continuous, which you differentiate on x1 to xs. And examples for these are Bessel functions. They have an index and an argument, and one is discrete and the other is continuous. And most of the orthogonal polynomials like Legendre, Jacobi, and so on. So here's an attempt at a definition that tries to mimic what we have seen before. So if we have such a multivariate guy, f, we call it D-finite if there is a finite set of basis functions of this form. So we take the function f, we apply certain shifts to the discrete variables, we take certain derivatives with respect to the continuous variables, and if this set for certain integers I1 up to is, j1 up to jr, if there is a finite set of such basis functions such that any instance of my function where I allow arbitrary shifts, maybe by 100 or 1000 and high derivatives, if any instance can be reduced to this finite set as a linear combination of these finite set of basis functions, then we call the function multivariate D-finite, and it has analogous properties. Again, it suffices to specify finitely many initial conditions to define the function uniquely, and we can store it in the computer in a reasonable way. Then, of course, we can do the multivariate extension of our operator algebras, and in general this is called an ORE algebra, so we can now have dx, Sn, and whatever being mixed in the same algebra. And we define the annihilator of a function to be the set of all operators p from this operator algebra such that p applied to f is 0. And it's not difficult to see that this forms a left ideal. So if we have an operator that kills f, if we multiply this operator from the left with something, we get an operator that still kills f, so it is still in the annihilator. So that's why it's a left ideal. Yeah, and in computer algebra, once we talk about ideals, we like to use the concept of Gröbner basis. I don't know how familiar you are with Gröbner basis, and I definitely don't have the time here to really explain what it is, so you have to take it as a black box. Just to give you an idea, here's an example. So the Legendre polynomials, they satisfy the three-term recurrence, second-order recurrence in the first line, and in the second line, and the second-order differential equation that is written in the first line. So we have seen how we translate this into operators. And actually these two operators, they generate the whole annihilator of this function. However, they do not form a Gröbner basis. If we compute a Gröbner basis, we get something else. Well, the second one is still the same, the differential equation, but this now turns into a mixed equation. So we can compute Gröbner basis by the Buchberger algorithm, and they have very nice properties, very useful properties, because mostly what we will use is the fact that when we have specified this annihilator, this ideal, by a Gröbner basis, we are able to decide whether a given operator is an element of this ideal or not. And we will use this in the way that when we make an ansatz with undetermined coefficients, we can apply this decision procedure, and this gives us constraints for the unknowns such that something is in the ideal. So this will turn out very useful for the creative telescoping What is this? Okay, this is again the definition of multivariate D-finite, now stated in algebraic terms. Yeah, actually, we don't really need this. Just to show you this. This is the typical picture that you draw with Gröbner basis. So let's say we have the two operators, dx and Sn, like here, and nothing else. Then we can draw this two-dimensional picture. Here we draw monomials in dx direction. When I make a cross here, it means there is an operator that has a leading monomial that is dx cubed. And there's some other operator that has a leading monomial Sn squared. And there's another one that is here. And all the monomials where we have dots here, they are so-called irreducible. They are under the staircase. You can think of a staircase here. Yes. And they are below the staircase, and somehow their number characterizes how complicated this function is. So we call it the holonomic rank of the function, and the higher the holonomic rank is, the more complicated it is to deal with this function. Let me skip this. Yeah, closure properties, I don't want to spend much time. They are the same as before, now applied accordingly, depending on whether we have discrete or... Okay, so what is creative telescoping? I should come to the main point before the time is over. Let me first explain it in the discrete setting. So I assume that Fn, k, is a bivariate D-finite sequence, and we know its annihilator, and we want to compute a creative telescoping relation that is a relation of this form. So on the left-hand side, we have a linear combination of f and its shifts in n. So the k is always k. K is not changed. Only the n is shifted, and the coefficients in front of this linear relation are polynomials in n only. Again, no k here. And on the right-hand side, we find the antidifference of some other function gnk. So, and antidifference with respect to k. So k plus 1 minus g of k. And the first question that one can ask, so what is this function g? In which set or in which space should we look for this function g? And if we make no restriction, then you can just write down trivial solutions by just reformulating this thing and write down something, but that doesn't mean that you found something. It's just a trivial rewriting, so this is definitely not interesting. But it turns out that a reasonable choice where you want to search for this function g is the set of all functions that you get from f by applying shifts and differentiations, whatever operators you have at hand. And so this leads us to the following ansatz. So we define P, the operator that describes the left-hand side. So in operator notation, it's this. It's the shifts in n. And we want to find an operator Q in this Ore algebra such that P minus Sk minus 1 times Q annihilates F. So this is exactly the relation above. This is the left-hand side, and here we have Sk, and the G is assumed to be Q times Q applied to F. Yeah? And so we have to decide for a given R, does there exist such a P and Q in the annihilator? And here now we use the theory of Gröbner basis to compute such things. Because we make this ansatz and we apply the condition of Gröbner basis that this operator with undetermined coefficients is in the annihilator, and this gives us conditions on the, actually linear conditions on the unknowns, well, at least on the unknowns in P, the P's, and other conditions on the coefficients of Q that we can solve for. This is the same thing in the differential case. And this example is actually not so interesting. So how do we compute it? As I said, we make an ansatz So this operator P is called the telescoper, and the Q is called the certificate. As I said, we fix an integer, an order R, this we don't know a priori, and we make this ansatz with unknown coefficients. And for the certificate, we again use the knowledge from the Gröbner basis. Namely, we have to identify which are the monomials under the stairs, because every operator, wherever it lies, can be reduced to a linear combination of these 5. So it suffices to include these 5 in our ansatz. So we write Q as a linear combination of these monomials that are under the staircase with undetermined coefficients that now can contain everything. So here is the ansatz. Okay, so this is in the differential setting. We have here the dy. And now you see the problem, what happens when we bring this into the normal representation, where we write all the d's on the right. We have to commute here, and this will introduce a derivative of this q. So here you see the derivative. And that makes the system that arises a bit difficult to solve. Because so the p's, they just appear linearly, but the q's, they appear with the q themselves and their derivatives. So this is in the end a first order coupled linear system of differential equations, but luckily there are algorithms to compute the solutions of such systems, and they are employed. And what we get in the end is what is called Gisak's algorithm. That is a generalization of Zeilberger's algorithm for a hypergeometric summation. So the original motivation to introduce this holonomic systems approach was to prove special function identities. So let me demonstrate how this works in practice. So if you open one of these books, you see 1,000 pages of formulas. Okay, let's zoom in. Yeah, this is the whole book at one glance, and you see it's just formulas. Every page contains formulas, and so now we have such formulas. So which one you want to pick? Yes, let's take this one. Okay, and so this is a typical entry in this book. How can we prove it with creative telescoping? First, we have to identify what are the constituents of this formula. So these are the Gegenbauer polynomials. We have to look them up and know what differential equation they satisfy. Okay, the gamma function we know all, and this is the Bessel function. Well, and so let's prove this. Here I copy this identity. On the left-hand side, we have an integral. That means we have to do creative telescoping on the left-hand side. So we enter the integrand into the command creative telescoping. This is in the package holonomic functions that I implemented in Mathematica. And so here we just copy this expression in Mathematica notation. Then we have to say that we want to integrate with respect to x, and we have to specify which of the other variables or parameters we want to consider. So we choose to consider the shift in n and the differentiation with respect to a. And we decide to ignore the nu. This is just a random choice. You can play with this. And then after a few moments, you get this output. And in the first two lines, you see, because now it's multivariate, we compute several relations. So the first line is a telescoper P1. The second line is another telescoper P2. They are constructed in a way that these two again form a Gröbner basis of an annihilating ideal for the integral. And in the third and fourth line, you get the corresponding certificates, a Q1 and a Q2. So then you should do some checks that when you evaluate at the boundaries that everything vanishes, and you turn to the right-hand side. Here there's no integral, so no need to do creative telescoping. We can just call annihilator that executes the closure properties on all these on this combination of known functions. So we really just have to copy this expression, again specify which operators we want to consider, and instantaneously we get the equations that define the ideal of this, that define this annihilator. And now if you compare, you find that this output is the same as the first two lines here, and you do some initial value checking to establish a proof. Okay, I don't want to talk about diagonals of rational functions, but in the last 5 minutes I want to get back to the balanced binary matrices because I have used them so much for illustration purposes. So here's a theorem that says for any fixed k, the sequence bk that counts balanced matrices of dimension 2k times 2n is p-recursive in n. How can we see that? It's not so difficult. So we use the elementary symmetric function in 2k variables of degree k. So this is this. And we observe that each monomial in this symmetric function corresponds to one column in our matrix, to a choice of placing k1s and k0s in a column of length 2k, each monomial of this symmetric polynomial. So if we take a power, ek to the 2n, we get the weight enumerator of all 2k times 2n matrices that are column balanced. And since the number of ones in each row are counted by x1, x2, and so on, we can extract the coefficient, because we want to have that when the matrix has 2n, that there should be n ones in each row. So that corresponds to picking the coefficient where all variables have power n in this power. Then this coefficient tells us how many matrices among these column balanced are there that are also row balanced.
So it looks like you keep the slide on diagonal, but now you need that.
Well, yeah, no, it's a... So this is what we found, and we can write this in different forms. So we can say this is a constant term extraction of this rational function to the power n, and this can be converted into an integral, actually a multivariate integral, and this is enough for, I showed you how to do integrals, so you should be happy with this representation, and you can ignore that it can also be written as a diagonal. It's not necessary here. Okay, and using this approach, we can find this second, or we can provably find the second order recurrence for the number of 4 times 2n balanced matrices. I should say that all this work on balanced matrices is with these co-authors, Robert Doherty-Bliss, Natalia Tersakov, and Doron Zeilberger. And here is an exercise. Derive this recurrence using creative telescoping. If you have a lot of time, you can also do the next case. This one that I showed already. So far we had only a guess. Now, doing this approach with creative telescoping, we can derive this recurrence in a provable, rigorous way. And last slide, if we add the condition, as it was in the puzzle, that certain patterns are disallowed. So we define two sets of patterns, H and V. In the example that we had with the puzzle, they were the same, but they could be different patterns in 0, 1. And we have B of n, the number of balanced 2k times 2n binary matrices that avoid in the horizontally the patterns in H and vertically the patterns in V. Then also this sequence is a p-recursive sequence. How can we see this? Again, we do a weight enumerator of such matrices. So if we have a 2k times n, it's here is written for n matrix, we put the weight t to the n, so t gives the number of columns, and x1 to the a1 and so on it defines the number of ones in the ith row. So similar to before, just that now we also have the t. Now I have to hide the details. There's something called the transfer matrix method to find the weight enumerator of the set of all matrices that avoid these patterns. Not yet talking about the balancing condition. This will be a very complicated rational functions in all these variables. And in the end, we have to extract the coefficient to get what we want, to count such matrices that avoid the patterns and are balanced. And if you have a lot of time, you can work out the details and do this computation for matrices of dimension 4 times 2n that avoid the patterns 0, 1, 0 and 1, 0, 1. Okay, my talk consists of 3 parts. That's the end. Thank you very much.
Are there any questions? This is supposed to work, but I don't know how. Yes, it does. So, any questions? Come on. Yeah, we have exercises, but if you don't ask the questions now, you won't be able to do the exercises. At some point, you mentioned that you had 2 operators that annihilated a given, I think it was a Legendre polynomials, and you said actually they generate the ideal. And is this, how do you prove this?
This is not obvious,
okay.
A priori. This is not at all obvious. You see it then when you compute the Gröbner basis, you find that these 2 operators imply the third one that came with in the Gröbner basis, the mixed one, which then leaves you with something of holonomic rank 2. And then if you know a bit about these Legendre polynomials, you know that 2 is the minimum possible that if the annihilator had dimension 1, holonomic rank 1, that would mean that it would be hypergeometric. And it's well known that the Legendre polynomials are not hypergeometric. So the next possible is 2, and if you reach this, then you know you have everything. But in general, of course, it can be very non-trivial to decide whether a given set of annihilating operators is the complete annihilator or if you're still missing something.
May I make a related question?
Of course.
Just to test if I understood or not, when you showed us that rank diagram with 5 bullets and 3 crosses, right? There was at some point.
Yes.
I thought, I imagined that if you know the crosses, you know that there are regions where you don't need to search.
Right.
Because these crosses must make
so
a
this is the
path or something like that.
This is the condition on D-finiteness. If the crosses are located in a way that only finitely many bullets are below the crosses. So somehow the imagination is that every cross spans a cone, a quadrant that has its corner. So this cross deals with everything that is in this quadrant, right? It cuts out everything here, and this one cuts out everything here, and so on. And imagine if that cross was not here, but was sitting here, then you would get an infinite line of bullets and indicating that this annihilator does not define a D-finite function, right?
But having something like that tells you that certifying that a set of generators is complete is a finite search.
Well, yes, right. You can. That's correct. So if you assume that this is not the full annihilator, you can say, well, then there must exist a relation between these 5 bullets. So you could make an ansatz with your function modified according to these bullets, and if you find a linear relation, but then it depends on how your function is given, whether you can compute such a thing, whether you are able to simplify this in a way that you can decide a linear dependence. But yes, I mean, this is also what we do with guessing. If we find something and we are not sure whether this is really the smallest one, well, what you do is you try to make an answer with these. The only problem is then that you don't know the degree. The degree can, of course, be quite high. But yeah, you try to search a linear relation among those. And well, if you don't find with reasonable effort, you are kind of confident that you have the full annihilator.
Okay, thank you again.